In today's lesson, we're going to be looking at limits of trigonometric functions. Before we can get to limits of trigonometric functions, we want to just take a look at some very basic ones. You'll see right here we have a graph of our sine of theta function, and what we want to do is take the limit as theta goes to 0. Well, as theta goes to 0, whether I approach it from the right-hand side or whether I approach 0 from the left-hand side, in both situations my function is approaching 0. So the limit as theta goes to 0 of sine of theta is 0. Using the same idea here, we can take a look at the limit of theta going to 0 of cos of theta. Well, as I approach 0 from the left-hand side, my limit is approaching 1. As I approach 0 from the right-hand side of cos of theta, my limit is also approaching 1. Therefore, the limit exists, and the limit as theta goes to 0 of cos of theta is 1. So we're going to use these two results later on in today's lesson. What the squeeze theorem says, if you have a function f at x that's less than or equal to a function g at x, which is less than or equal to a function h at x, if this happens at a value of x that's near your limit, in this case your limit is approaching a, and the lower bound and the upper bound both approach the same limit L, let's say, as x approaches a, then that middle function will also approach L as x approaches a. Visually what that means here is, let's say you have your function h at x, this is your upper bound. You have your function f at x, this is your lower bound. In between those values, this is your function g. Now, the function h, as x gets infinitely close to a, is approaching some limit L. And likewise, the function f, as x gets infinitely close to a, is also approaching some limit L. By the squeeze theorem, your function g must also approach L. We're going to use this result for the next proof. Let's take a look. All right, so here's our goal. We want to prove the following result. The limit as theta goes to 0 of sine theta over theta is 1. First observation here is we have the following inequality. So let's go ahead and justify why this is true. The area of OBD is less than the area of OBA is less than the area of OCA. So what we have here is this is our unit circle, right? We have our unit circle, and we've defined our sine and cos about the unit circle. And what we have here is the area of OBD would be this area right here. And the first claim is that the area from here to here is going to be less than or equal to the area of OBA. And I think we can see from an area standpoint that that would be true. The second condition, this one right here, is saying the area of OBA, so that's the right angled triangle right here, is the case that it must be less than or equal to the area of OCA, which is obviously true as well. So what exactly are the areas of these shapes? Recall that the area of a sector is 1/2 the radius squared times theta. So in this case here, area of OBD is a sector of our circle here, and what that would be here is the area of OBD would be equal to 1/2 cos squared theta times theta. Notice here the radius from here to here would be cos of theta. The area of OBA is just a triangle, and the area of a triangle is 1/2 the base. The base here is cos of theta, and the height of this triangle is sine of theta, just by definition of cos and sine. So we have our area of OBA. And the area of OCA is another sector of our circle. And in this case here, the area of that would be 1/2. The radius in this case would be 1 squared times theta. So this would just be theta over 2. So now, subbing these values into our inequality, you can see here that the halves cancel all the way across here, and we're just going to be left with cos squared theta times theta is less than or equal to cos theta sine theta, which is less than or equal to theta. Now we're going to go ahead and divide across by theta cos theta, in which case this will simplify to become, now we're going to go ahead and take the limit of all sides of the inequality, and we get, notice here we have our function g at x bounded below by cos theta and bounded above by 1 over cos of theta. And then furthermore, notice the limit as theta goes to 0 of cos of theta is 1, and the limit as theta goes to 0 of 1 over cos of theta is also 1. So therefore, by the squeeze theorem, we have the limit as theta goes to 0 of sine of theta over theta is equal to 1. We've now got a very important result that we can use to solve limits of trigonometric functions. Let's take a look at some examples. So for our first example here, we want to take the limit as x goes to 0 of sine x over 2x. What you want to do is you want to make your limit and adjust it and use the following fact. I want to use the fact that the limit as x goes to 0 of sine x over x is 1. So I want to use the result that we just proved and sort of adjust that function when necessary so I can apply this rule. Well, I can factor 2 out of the expression, in which case I'm taking the limit as x goes to 0 of sine x over x. But now we know that the limit as x goes to 0 of sine x over x is 1, and the answer to example number 1 is a half. Let's take a look at another. So same idea with this question. I want to be able to apply my limit property that we discovered. So how can I adjust this so that it fits? Keep in mind the x is just a placeholder. Essentially what it's saying the limit of your angle, as your angle goes to 0 of sine of the angle over the angle, is 1. This does not have to be an x. It can be a combination of expressions. As long as it's the same value in the top and bottom, then that limit will tend towards 1. What I did here first was I added a 2 in the bottom so we can have the same measure in the top and bottom, and then I made up for that by putting a 2 out in front. Notice the 2's will cancel and the question's unchanged. Now, if you're asked to evaluate the limit as x goes to 0, that would be equivalent to evaluating the limit as 2x goes to 0. And in which case here this becomes 2 times 1, and the answer for example 2 is 2. Let's try another. So for this example here, let's try the same trick. Now notice here we've done the same trick here. I've inserted a 7x on the bottom and made up for it by putting 1 in the top, and likewise a 4x on the bottom, made up for it by taking the 4x at the top. So the question's unchanged. Now what we're going to do here is use our limit properties. I know the limit of the product of functions, so in this case here, I'm treating the 7x over 4x as one function, and this expression as a second. Well, the limit can act on each of these individually, and that's what I've done here. So if you'll notice here, we take the limit as x goes to 0 of 7x over 4x, and then evaluating this limit here. Continuing, this becomes, and now making the observation here, we can factor the 7/4 out of the limit, and then x over x would cancel to become a 1. And again, keep in mind, we're taking the limit as x goes to 0. It's not equal to 0, so therefore those will cancel, you get a 1. Here, the limit of the division of these, you can take the limit of the top and bottom. And again, I interchange the limit as x goes to 0 is equivalent as the limit of 7x going to 0. And saying that x is going to 0 is also equivalent to saying that 4x is going to 0. Now we can go ahead and apply our limit properties, in which case this becomes 7/4 times the limit as x goes to 0 of 1 is just 1. And this expression would also be 1 over 1. So the final answer for this example is 7/4. Let's try another. So for the next example here, we're taking the limit as x goes to 0 of this expression. There is no sine function incorporated in this question here, but notice here, if I let x go to 0 and I sub this in, we get 0 over 0. So I need to do something to get some cancellation here and apply my limit properties. Well, in this case here, what I'm going to do is I'm going to multiply the top and bottom by the cos of x plus 1, in which case this expands out to be, and recall here we have sine squared x plus cos squared x is 1. Therefore, cos squared x minus 1 is negative sine squared x. So I'm going to get rid of that, and that'll add a sine function into this expression. Breaking this limit up here, what I've done is I've taken the sine squared of x and broke it up into negative sine x and sine x, and then likewise put the x part of this expression here and the x plus 1 in this expression here. So now if I go to take my limit here, this will be the limit as x goes to 0 of negative sine x over x, which in this case is negative 1. And notice here, if I let x be 0 here, we're going to end up taking the limit, and this will be 0 over 1 plus 1. So this will be negative 1 times 0 over 2, which is 0. So the limit of cos of x minus 1 over x is 0. Let's look at another. For example 5, we need to show that the limit as x approaches pi of sine of x divided by pi minus x, we have to find what that equals. Well, recall, consider the unit circle and consider the terminal arm measured at an angle of x. By definition, the length from here to here would be sine of x. If you consider the acute angle in the second quadrant also having a measure of x, then the measure from here to here would be pi minus x, in which case, by definition, the length of this leg of the triangle would be sine of pi minus x. But as we know here, both these lengths would be equal, so the sine of x is equal to the sine of pi minus x. So now we're going to take our limit, and we're going to go, the limit as x goes to pi, replace the sine of x with the sine of pi minus x, and put that over pi minus x. And now you can see here we almost have the same form that we want, sine theta over theta, and the limit as theta goes to 0. We just need this limit to go to 0. Well, saying that x approaches pi is equivalent to saying that pi minus x is approaching 0. So therefore we can change this to the limit as pi minus x approaches 0 of the sine of pi minus x over pi minus x. In which case here, by definition, the limit of this expression would be 1. All right, that concludes today's lesson. Please review these examples here and take a look at the proof. Thank you.